Welcome to Digital Gravity Lab. I am Matthew Isler, a Doctor of Philosophy student in Computational Sciences and Engineering at Harrisburg University. So this video is going to summarize my paper on parallel programming changes from 2018 to 2025, and while the changes matter for USD, Universal Scene Descriptor, native simulations in the NVIDIA Omniverse. So little bit of context here. This is my first post, but I will be making these every single week for the rest of this semester, and will continue throughout my doctoral program here. What I would like to note first is there's a saying attributed to Albert Einstein that if you can't explain it to a 6-year-old, you don't understand it yourself. There's a good chance that as they learn, these videos will get a little bit better, because I'll get to that point where I can explain a lot of this to a 6-year-old. But as of right now, I will do my best, and let's get into it. This channel is going to feature 15 to 20 minute videos on my assignments every week. So I'll be posting summaries of my videos. In the future, I might not be using PowerPoint. I might be actually just sharing a screen and walking through some of my papers, or whatever code it is that I need to write and run for that week. After this semester, it's going to pivot to kind of a 4-stage research plan that I have leading up to my dissertation for my PhD. This week is just going to focus on my this paper that I just wrote, and I kind of rebuilt some slides for it for now. And but this week, Kaylin will kind of mean transparent, reproducible progress, and you'll kind of see my results as I kind of get to that. I can explain it to a 6-year-old point. Again, work with me until then. Just showing a little snippet of my paper here. You can kind of see parallel programming models and methodologies, 2018 to 2025 innovations, the state of the art with implications for USD native simulation platforms like the NVIDIA Omniverse. So we'll get into what this is about. So the paper I just wrote focuses on the updating of the 2020 baseline by Sarnal and colleagues, and asks what materially changed from 2018 to 2025 in parallel programming models. So this contribution had reframed paradigms, extending comparison tables for portability, heterogeneity, tooling, resilience, and energy, and then added a whole section on the Universal Scene Descriptor or description, the USD native research vehicle, which I'll be implementing in the NVIDIA Omniverse. And there's kind of that baseline that was done in 2020, which organized programming into shared memory, distributed memory, partitioned global access space. And so I extended some of those tables with some of the modern new updates that's come up in the last 5 years or so, and the various GPU aware communications, which is improved. And so the next step, I'll condense that paper into one slide and unpack some of the new updates. Okay, so here's my one slide takeaway. So first, heterogeneous, the graphics processing unit accelerated nodes are kind of the default target. So assuming you're running with a combo of GPUs and CPUs. Second, portability stacks matured. Cocos, Raja, Kona single source C++ model, widely known as Cycle, and Open Multiprocessing, OpenMP 6.0. So it's been about 2-3 versions since the paper in 2020. So that offline driver, variable cross-vendor pass, so it's a little bit easier to communicate across vendors. Communication became accelerated rare, so MPI 5 added sessions and persistent or partitioned collectives. There's a unified communication X, which underpins the transports, the NVIDIA collective communications library, NCCL, NVIDIA shared memory, system, NFSHMM. They simplify multi-GPU patterns. For tooling, reproducibility has improved, so report time to solution and energy to solution together. There's a little bit of more information there, and just kind of what I've kind of been working on. So operating all of this in Open Universal Screen Description, OpenUSD, and the NVIDIA Omniverse, as my long-term goal is working with the NVIDIA Omniverse. So I'm kind of doing my best to frame everything I can around it as far as I work in this computational sciences and engineering program. So let's looking at these one at a time for what specifically changed between 2018 and 2025. So in high performance computing, the hardware reality is that single thread gains have slowed. So individual cores are not rapidly increasing in speed as much as they used to. But beyond that, you've been having the multi-core CPUs being paired a lot more with many core GPUs that have thousands of cores, and adding a lot of RAM to that, and RAM being associated with different types of cores even within a GPU, and having different rates of how different cores of and sets of RAM store and communicate across that. And so in the software side, they're kind of putting that parallelism in the different software, kind of rising to the surface, and having to deal then also with the locality. Where is the RAM? How close is it to different cores in the GPU and CPU? And then there's this broader ecosystem shift for Universal Scene Description, USD, having a lot of native platforms that work with it, like the NVIDIA Omniverse, and those work with photorealistic, physics-driven simulation that, trained autonomous cars, trained autonomous robots. And then of course you have the drastic shift with ChatGPT and all these different GPTs and the AI that can be run on a GPU that CPUs just don't have anywhere near the processing power for. I mean, you're talking about CPUs with 30, maybe even less, 64 cores, with GPUs with thousands of cores. And so they've been taking these programs and adding parallelism to as much of it as possible. And so all the algorithms have to consider that, and the traffic and the communication that happens, not just across a single CPU or single unit, but hundreds and thousands of units, and how they communicate both within a node and across nodes. So going into those standards and libraries, which have matured as well. So some of these standards and different libraries, right? Open multiprocessing MP shifted from 5 to 6, which has stabilized some target offloading, interoperability with tasks and reductions. So it's made more directive-based offloading realistic. Message passing interface 5 has come out, right? That introduced sessions and persistent repetitions collectives, which reduces some of that orchestration overhead, enabling some overload. There's various portability stacks, adding different code that goes across vendors and improves performance as long as you have the right compiling software backends. Various communication processes. I mean, most of the market is NVIDIA, but not all of it is, and you are communicating between other CPUs and other softwares and processing units. Even within a particular GPU, you have different types of cores. So knowing how to send things across different cores requires different code and standards. And some of the tooling is continuous integration, continuous delivery, improved, and even the energy and resilience has just come first class and has allowed a lot of different programs to work a lot better, not crash as often, um, and also the work between the different codes has been improving drastically. So zooming in some of the communication and runtime fabrics. Okay, on the communication and runtime side, MPI 5 and even starting from 4, which came out a few years ago, it's allowed for some persistent and partitioned collectives, so sets of data, to kind of be held and allowed to be able to rerun a little bit and reused. And so that partitioned communication has basically allowed a set of RAM and information to be set up and kind of refed and allowed that information to be able to reused a bunch of times. And so that has really been great for multi-threaded processes. And then the different NVIDIA collective communications library, they give a lot higher throughput for multi-GPU systems to all be able to reduce the amount of power stuff it uses and to broadcast easier across multiple ones. And then there's also different one-sided puts and gets across various memory sets that has been useful when the collectives are mismatched, so it can kind of understand which one to use and when to use which. And so the various patterns and things that can be used. And when you need fine-tuned device-initiated exchanges, they've improved that so you can observe it a little better and reproduce the exact same set of information again. Okay, so some of the various tools have improved. So NVIDIA Nsight Systems Compute, the High Performance Toolkit, the HPC Toolkit, Intel vTune, and others. Now they correlate host and device timelines a lot better. So you can kind of see where your time and your bytes and your go and the time it takes to process things. There's a lot better improved reproducibility, particularly with the NVIDIA Omniverse. So where you can containerize builds, the physics, and record seeds. So to rerun different physics things, you can store that physics variability across it, and store different stages with versioning, and be able to kind of expect that variance and report those confidence intervals. So there's a lot more information being stored when you're running things and tracking everything on the GPU. It also is reporting better energy, right? So you know how much energy your codes are running. So different physics simulations, things like that, right? And you can kind of cap power to even particular processes. And sometimes it takes longer to run, but overall, you might get better power efficiencies. So that's been pretty important. So without some of those measurements and things like that, you just can't compare what you do with one machine with another one. And if you run the same thing, you won't know why it does something different this time versus last time. So that really helps with protocol in physics. So, but why am I running this in the NVIDIA Omniverse, right? So let's get to that. Or maybe I should say, why do I want to run all this stuff and learn more about this for the NVIDIA Omniverse, and why have I already been using it? Well, the NVIDIA Omniverse offers a whole set of non-destructive layers, and then timelines for processing physics and rendering, and using OmniGraph, you can kind of process all of that and build in different codes so that you can just in time, compile it to the CPU or GPU, integrating it all together with the various codes. And so, kind of as I get this whole PhD and learn all this computer science stuff, I'm going to be better able to optimize the back end and kind of know what these different nodes and schemas do at the back end as we're processing the various physics for that. And in that whole thing, you kind of hold a scene constant, but vary the programming and kind of like what GPU, CPU send things to get apples to apples comparisons across modules and CPUs. And so there's a whole practical stack um, that I'll be able to demonstrate throughout this whole program. Okay, so here's kind of a snapshot of what I kind of know that I could use within the Omniverse. Obviously, just starting with the Compute Unified Device Architecture, CUDA, and Warp, basically tightly coupling everything within the NVIDIA Omniverse. However, as I spread beyond that, or I run it on much larger systems and I process a lot more, then I might have to utilize some of the other libraries for passing out information to other processing units instead of just my one computer. And so there's a whole system within that. And of course, if I'm using other GPUs as well, then there's kind of this portability path that I'll have to follow as well. A few random things that I can measure, particularly within the Omniverse, but kind of what a lot of the computer science is all about. Measuring things to time to solution, right? How long it take to process, how many steps per second it does, right? If you spread it out, distribute it across many more cores, how much is your GPU or your desktop or broader server being utilized, and how much energy does that take? Can you cap the energy level so that it might just take a little bit longer for whatever process you want to run, but overall it uses less energy. The portability, right? How easy it is to move and use different type of processors and graphics cards or type of cores within a GPU, etc. And how stable is it when I'm running physics simulations and things like that. And hey, can I reproduce it? If I run the same physics simulation twice, is it going to do the same thing? Well, there's a whole seeded run for that, so I can test that within USD. And obviously, when I'm testing things across GPUs, testing compatibility, well, some things are going to be workload specific and sensitive to various driver versions. So if anyone is following my work or doing similar things, make sure you check that. Check the documentation because it might not work with a different driver or GPU, etc. I'm going to be running this, doing these posts every week, and I'll kind of be pivoting towards that 4-stage thing, which I'll talk about in a second here. But yeah, basically as I go through this, I'll grow. So note at the beginning, I'm probably not going to do this whole PowerPoint thing. I might just read through whatever paper it is I ran in the future, because this whole PowerPoint thing is actually a lot more work. So move forward. Brief note here on my future work. I'm actually going to work and build out several things as I learn about parallel processing and build the larger system. So I am going to be looking at some bonded unit micromechanics, think chemistry modeling type stuff, and working in microgravity, basic simulators. I'm going to develop some things for building Lux blocks. You can check out the website, download this PDF and check that out, or just Google them. And I also have a pending patent for flexible modular architecture and assembly system. So that is somewhat like Flexo if you want to go look that up. And so I'm going to be working on that and a way to simulate that before I get to the major goal, which is a centrifugal gravity space ring platform for training robots in a rotating frame assembly and inspection stack. So you will hear more about that in the future. Thank you for getting through my first video post here. I hope you'll subscribe to Digital Gravity Lab and it becomes even more interesting and useful to you in the future. I will be having more posts every week. Please comment, give me questions. I will do my best to reply to everything that you post. Check the links to all this information for further study if you're interested. Thank you again. I'll see you next time at Digital Gravity Lab.